Now, today we're going to continue with the logic of quantified statements with statements with multiple quantifiers. So when a statement contains more than one kind of quantifier, we imagine the action suggested by the quantifiers as being performed in the order in which the quantifiers occur. So, for example, for all x in set D, there exists a y in set E such that x and y satisfy the property P of x and y. You must be to show it's true. You must be able to meet the following challenge. First, select any element x, and then find an element y that is true, that satisfies the property P of x, y. Because you do not have to specify the y until after the x has been specified, you are allowed to find a different value of y for each different x you are given. So, again, with the Tarski's world, these slides can get kind of confusing, going back and forth between the examples and the diagram that's only on one slide. So I'm going to skip the Tarski's world slides. If you want to go back and look at them, the slides are on Canvas in the Files section. You can go through these examples and follow along yourself. I'm not going to go back and forth. That's just too time consuming and might be confusing if I go at a pace that's not suitable for an individual. So, interpreting statements with two different quantifiers. If you want to establish the truth of a statement of this form, pick whatever element x and D, then find an element E that works for that particular x. If you want to establish the truth of the statement of this form, you might find a particular D that will work no matter what y is in E. So there exists a D, an x and D, such that all y works. All y's in E work in the P of x and y. This example is the cafeteria line has 4 stations: salads, main courses, desserts, and beverages. The different stations offer different options. 3 students, Uda, Tim, and Yuan, go through the line and make the following choices. These choices can be shown in this diagram here, where you have each option and who chose which of the options. And so write each of the following statements informally and find its truth value. There exists an item I such that all students S chose I. So basically, there is an item that all students chose. B, there exists a student S such that all items I, S chose I. That means that there exists a student, there is a student that chose every item. which is false. There exists a student, C, there exists a student such that all stations Z and there exists an item I in Z such that S chose I. There exists a student such that they chose, there is a student that chose an item from each station. From all stations. D, all students and all stations where I is an item in each station such that S chose I. There's this, all students chose an item from all stations, which is false because UN didn't choose a salad. But these are the solutions for those A, B, C, and D. But now translating from informal to formal language. Most problems are stated in informal language, but solving them requires translating them into more formal terms. For example, the reciprocal of a real number A is a real number B, such that A times B equals 1. The following two statements are true. Rewrite them formally using quantifiers and variables. Every non-zero real number has a reciprocal. And there is a real number with no reciprocal. So, with two quantifiers, for all non-zero real numbers U, there exists a real number V such that U times V equals 1. For B, there exists a real number C such that for all real numbers D, C times D does not equal 1. And that real number C would be 0 for that in that particular instance. Now, the definition of the limit of a sequence uses both quantifiers, the universal and existential quantifiers, as well as the if-then conditional. We say the limit of a sequence A of sub n as n approaches infinity equals L, and write this formula here. If and only if the values of A of n, A sub n, become arbitrarily close to L as n gets larger and larger without bound. So, more precisely, this means that any given positive integer or positive number epsilon, we can find a number capital N such that whenever small n is larger than capital N, the number A sub n sits between L minus epsilon and L plus epsilon on the number line. Basically, as little n gets larger, epsilon gets smaller. As n approaches infinity, epsilon approaches 0. Symbolically, this is how it would be represented. And the authors admit that the logical complexity of this definition it is no wonder many students find it hard to understand. But limits, that's Cal 1, right? Yeah. Got to understand those before you can understand differentiation. Ambiguous language. I don't know why this slide is in here, but you got to be careful of ambiguous language like this picture here. Depending on how you look at it, it could be looking at the profile of a young lady or the face of an older woman with a large nose. So, like I said, it's just kind of a one-off slide. I don't know why they put it in there, but negations of statements with more than one quantifier. Now, last time we saw that the negations of single quantifiers were you basically change to the other quantifier and invert the condition. So it goes from a negation of a universal quantifier is an existential quantifier such that not p of x. Likewise, the negation of the existential quantifier is the universal quantifier such that p not p of x. So when you combine these together, you get the if you have the universal quantifier first and then the existential quantifier, you go to the other one, the existential quantifier, and invert the existential quantifier, which ends up being which ends up being the existential quantifier followed by the universal quantifier and the inversion of p. Similarly, in the case of the existential quantifier coming first, the inversion causes this to go to a universal quantifier with the inversion of the second universal quantifier. That converts to the existential quantifier with the inversion of the p. So they're summarized here in the blue box here. So another Tarski world example. I'm going to skip over that. The order of quantifiers, very important. So consider these two statements. For all persons X, there exists a person Y such that X loves Y. As opposed to there exists a person Y such that all persons X loves Y. You're just changing the order of the quantifiers, but it changes the meaning dramatically. The first one says, for any person, it is possible to find someone whom that person loves. Second one, on the other hand, means that there is one amazing individual that is loved by all people. So the changing of the order of quantifiers can dramatically affect the meaning of the statement. If, on the other hand, if there's two quantifiers of the same type, then the order of the quantifiers doesn't affect the meaning. like the example of the commutative property of addition of real numbers. For all real numbers x and all real numbers y, x plus y equals y plus x. This means the same as for all numbers y and all numbers x, x plus y equals y plus x. Less formally, it's for all real numbers x and y, x plus y equals y plus x. So again, at the Tarski world, gonna skip through that. And we're losing light. Formal logical notation. Let's see. Come on. There we go. A little light so we can see. Okay. In some areas, computer science, logical statements are expressed purely in symbolic notation. For example, for all x in D, P of x can be written as, for all x, if x is in D, then P of x. Whereas the existential quantifier would be expressed as x is an element of D and P of x. So again, with the Tarski world, let's get through this. All right. The disadvantage of fully formal notation is that because it is complex and somewhat remote from intuitive understanding, when we use it, we may make errors that go unrecognized. The advantage, however, is that operations such as taking negations can be made completely mechanical and programmed on a computer. Get your calculator to do your work for you. Then taken together, the symbols for quantifiers, variables, predicates, and logical connectives make up what is known as the language of first-order logic. Anybody heard of the language prologue? No? It's an older language. It's short for programming and logic. A simple prologue program consists of a set of statements describing some situation together with questions about the situation. Search and inference techniques are built into the language that answer the questions by deriving answers from the given statements. It makes writing logical problems fairly easy. It's a fairly high-level language. Consider the following picture. G is gray, B is blue, W is white. G is above B1, B1 is above W1, W2 is above B2, which is above B3. So, you give it these statements to describe the picture and ask two questions about it. Apparently, the transitive property is not included in the language. So the is above xz if is above x is above y and y is above z, then x is above z. which is the transitive property. So, these relationships are and associations are made together. Is above G is above B1. B1 is above W1. G is gray, B1 is blue, B2 is blue, etc. And the questions are expressed using a question mark before a condition that you're looking for. Is B1 blue? And yes, B1 is blue. What is X, the X's that is above W1? And that would be what's above W1? B1 and G. So it would return 2 answers. And that makes it different than a function. A function only returns 1 answer, whereas this would return multiple answers, which some programs find Prolog difficult to wrap their head around because of the way the logic of the programs work. You ask it a question and you might get multiple answers, whereas under normal circumstances in most programming languages, if you give a function an argument, it returns 1 answer only. In Prolog, you can get multiple answers. Like I said, the color blue, B1 and blue, yes. And then it gives X as equal to B1 and G. So, but it infers the solution X equals G from the following statements. G is above B1, B1 is above W1, and the transitive property definition. Is B2 above W1? Answer is no. For what colors X is the predicate, W1 is colored X? The answer is X equals white. For what blocks is the predicate X is colored blue? True. The answer would be B1, B2, and B3. So, and that is it for section 3.3. We'll go to 3.4. The logic of quantified statements continues with a screen that doesn't want to cooperate today. All right. Arguments with quantified statements. The rule of universal instantiation is if a property is true of everything in a set, then it is true of any particular thing in the set. Basically, it indicates that the truth of a property in a particular case follows as a special instance of its more general or universal truth. So, the validity of this argument form follows immediately from the definition of truth values for a universal statement. Universal instantiation example. All men are mortal. Socrates is a man. Therefore, Socrates is mortal. So, suppose we're doing a problem that requires you to simplify r to the k plus 1 times r, where r is a particular real number and k is a particular integer. We know from study of algebra that the following statements are true. X of n times x of n equals x of m plus n. For every real number x, then x to the first power is x. So you substitute r for r to the first power. Then by this first argument, you add the two exponents and simplify, and there you go. Now the reasoning behind steps 1 and 2 are you substitute r for x, because r is a particular real number, and this applies to all real numbers by universal truth. Step 2, universal truth, is for every real number x and for all integers m and n, that is true. And r is a particular real number, and k and plus 1 and 1 are particular integers. This is true. This is in universal instantiation. Universal modus ponens, if you'll recall from chapter 2, it can be combined with a universal instantiation, and you can obtain a valid form of argument called universal modus ponens. So for all of x, if p of x, then q of x. P of a for a particular a is true. Therefore, q of a is true. Or less formally, like this. All right. Rewrite the argument using quantifiers, variables, and predicate symbols. Is this argument valid? Why? If an integer is even, then its square is even. K is a particular integer that is even. Therefore, k squared is even. That's true by universal modus ponens. You separate it out as two predicates in the premises. E of x, if e of x, then s of x for all of x. And then e of k for a particular k is true, therefore s of k is true. So this argument is a form of modus ponens, universal modus ponens, and is therefore valid. Write the conclusion that can be inferred using universal modus ponens. If T is any right triangle with hypotenuse C and legs A and B, then C squared equals A squared plus B squared. The triangle shown at the right is a right triangle with both legs equal to 1 and a hypotenuse of C. Therefore, C equals the square root of 1 plus 1, or 2, and therefore C is equal to the square root of 2. Use of universal modus ponens in a proof. Here's a proof that the sum of any two even integers is even. Makes use of the definition of even integer, namely that that an integer is even if and only if it equals twice some other integer. Or more formally, for all integers x is even if and only if there exists an integer, say k, such that x equals 2k. Suppose m and n are particular but arbitrarily chosen even integers for m, then m equals 2r for some integer r, and n equals 2s for some integer s. Therefore, m plus n equals 2r plus 2s. Factor out the 2 and you get 2 times quantity r plus s, and r plus s is an integer, and so 2 times quantity r plus s is even, thus m plus n is even. This is an expansion of the proof. Universal modus ponens is used multiple times to show that m equals twice some integer r, and to show that n equals twice some integer s, and if a quantity is an integer, then it is a real number. So r and s are real numbers. And then the distributive property is shown here to simplify 2r plus 2s equals 2 times r plus s. And then back to modus ponens again to show that r plus s is an integer. And then again to show that 2 times r plus s is even. Universal modus tollens. Another important rule of inference. Its validity results from combining universal instantiation with modus tollens. It is the heart of the proof of contradiction, which is one of the more important methods of mathematical argument. Formally, it's for all of x, if p of x, then q of x, and if not qa for a particular a, therefore not p of a. So the arguments can be used to show, this kind of argument can be used to show here, all humans are mortal. Zeus is not mortal, therefore Zeus is not human. And formalizing it here, at h of x is human, m of x is mortal, z stand for Zeus. The argument becomes what you see here. This is the form of universal modus tollens, and is therefore valid. I take issue with this statement. All professors are absent-minded. Tom Hutchins is not absent-minded. Therefore, He is not a professor. So, proving validity of arguments with quantified statements. Okay, long definition. To say that an argument form is valid means the following. No matter what particular predicates are substituted for the predicate symbols in its premises, if the resulting premise statements are all true, then the conclusion is also true. An argument is called valid if and only if its form is valid. It is called sound if and only if its form is valid and its premises are true. So, using diagrams to test for validity. All integers are rational numbers. So you can get kind of a Venn diagram thing going on with the two circles. All integers would be within the circle of all rational numbers. So use diagrams for the validity of the following syllogism. All human beings are mortal. Zeus is not mortal. Therefore Zeus is not a human being. So you have the major premise with the mortals enclosing all of human beings. Zeus is outside the mortal circle. Therefore, he has to be outside the human being circle. And combine the two, and you see that Zeus cannot be in the human beings set. Now use a diagram to show the invalidity of the following argument. All human beings are mortal. Felix is mortal. Therefore Felix is a human being. Not necessarily true, because Felix is somewhere in the mortal circle, but it's not necessarily when these are combined. Felix might be in the human being circle, but he might not. He could still be in the mortal circle without being in the human being circle. So either one of the situations might be the case. Therefore, it is not a valid argument. So converse error. That's what that was converse error. The form of the argument would be valid if a conditional statement were logically equivalent to its inverse, but it is not. And the argument form is invalid. We say that it exhibits inverse error. Equivalent to its inverse. That's the that's the next one. Inverse error is where if P then Q, if not and not P, therefore not Q. That's an invalid conclusion by inverse error. Use diagrams to test the following argument for validity. No polynomials functions have horizontal asymptotes. This function has a horizontal asymptote. Therefore, this function is not a polynomial function. The diagrams show that polynomial functions does not intersect the horizontal asymptotes, and this function is in the horizontal asymptote circle. Therefore, this function cannot be a polynomial function. There's no overlap. The argument is therefore valid. Creating additional forms of argument. Universal modus ponens and modus tollens were obtained by combining universal instantiation with those two forms. Additional forms of argument involving universally quantified statements can be obtained by combining universal instantiation with other valid argument forms, like universal transitivity. For all of x, if p then q, and for all of x, if q then p, or r, I'm sorry. Therefore, for all of x, if p then r, because of universal transitivity. Back with the Tarski's world again. Yeah, this one's a kind of a weird one. Have to rearrange stuff and all that sort of stuff. I'll leave that to do on your own time, but there's not going to be any Tarski's world questions on the exams or anything like that, so don't worry too much about them. Just a method of showing relationships and logical expressions and that sort of thing. Good for practice, but it's kind of tedious going back and forth between slides and stuff like that. Remark on the converse and inverse errors. One reason why so many people make converse and inverse errors is that the form of the resulting arguments would be valid if the major premise were a biconditional rather than a simple conditional. Consider the following. All the town criminals frequent the den of iniquity bar. John frequents the den of iniquity bar. Therefore, John is one of the town criminals. Not necessarily true. This would be an invalid argument because of converse error, and would be, if this were type of argument were to be true, it would be establishing guilt by association. The closer the major premise comes to being a biconditional, the more likely the conclusion is to be true. If hardly anyone but criminals frequents the bar, and John also frequents the bar, then it is likely, though still not certain, that John is a criminal. On the basis of the given premises, it might be sensible to be suspicious of John, but convicting him would be a no-no. A variation of the converse error is very useful for reasoning, provided it is used with caution. It is the type of reasoning that is used by doctors and auto mechanics. For example, here's how it would work. For every x, if p then q, if qa is true for a particular a, then check out statement p of a just because it just might be true. So you don't assume p is true when q is true, but it might be. So for the example with diagnosing pneumonia, if X has pneumonia, then X has a fever, chills, coughs, and feels miserable. And the doctor knows that John has fever, chills, coughs, and feels miserable. So doesn't necessarily mean he has pneumonia, but the doctor will probably attempt to gain further support for this diagnosis through laboratory testing that is specifically designed to detect pneumonia. This can be a tool for a diagnostic tool, including in programming. When a certain condition is true, you might expect another condition to be as true as well, but you have to check to make sure that the first condition is true in this. The first element is true, and verify it. But yeah, I believe that is it for the day. Was there any questions, or kind of went by fast because there was a lot of Tarski's World stuff in there that I kind of skipped over? I'm sorry? Yes. Yeah. The slides are already up on Canvas in the files section. So if you want to go through those and look at those more closely, or feel free. There's going to be a quiz on Tuesday for Chapter 3, so be here with your notes. And at the beginning of the class, I will also give you back your test 1. So have a good weekend. See you on Tuesday.